Hello students, this is Rahmat Ali from Indrapuram Public School. In the last session, we have learned about conductors, resistors, Ohm's law, combination of resistors, EMF of the cell, terminal potential difference and combination of cells. Today, in this session, we will learn about Kirchhoff rules, meter bridge, potentiometer and certain applications of potentiometer. Kirchhoff rules. As we know, Ohm's law is used for simple circuits. If we have complex circuits, then it becomes very difficult to use Ohm's law. So, Kirchhoff proposed two rules to simplify the complicated circuits. The first law is known as junction rule. It says that algebraic sum of the current meeting at a junction is 0. Here is a diagram which shows that the current coming towards the junction O is I1 and I2 and current leaving from the junction is I3. So, I1 plus I2 minus I3 is equals to 0. This law is based on the law of conservation of charges, and mathematically we can say summation of I equals to 0. As I have used the sign convention, which now I am going to repeat, that the current towards the junction is taken positive and away from the junction is negative. That is why in the previous diagram I have taken I1 and I2 to be positive and I3 to be negative. So, I said I1 plus I2 minus I3 equals to 0. Now, let us study the loop law. It says that in a closed loop, the algebraic sum of the potential drops is 0. This law is based on the law of conservation of energy. Again, there is a sign convention for this loop law. If the current is flowing from high potential to low potential, then the potential difference is decreasing, so we take the potential difference to be negative. Whereas, if we are moving in a circuit from low point to high point, then we can say that we are moving in the increasing potential, so the potential difference is to be taken positive. Now, we will study the Wheatstone bridge. If 4 resistors and the galvanometer are connected across a source of EMF forming a bridge, then the bridge is said to be balanced if the combined resistors are in proportion. Let us study the balanced condition of the bridge. Circuit for Wheatstone bridge. Let resistance P, Q, R and S are connected as shown in the diagram. A galvanometer capital G is connected across BD. A cell of EMF E is connected across AC. So, the current distribution is forming a bridge. If current from the cell is I, current through P is I1, then current through resistance R is I minus I1. If point B is at high potential, then current through the galvanometer is Ig as shown in the diagram. Then current through resistance Q is I1 minus Ig and current through the resistance S is I minus I1 plus Ig. Let us study the proof. For loop ABDA, I1 into P plus Ig into G minus I minus I1 into R equals to 0. For loop BCDB, I1 minus Ig into Q minus I minus I1 plus Ig into S minus Ig into G equals to 0. If the bridge is balanced, then Ig equals to 0. So, we get I1 into P minus I1 into R equals to 0. That means I1 into P equals to I minus I1 into R, equation number 1, and I1 into Q minus I minus I1 into S equals to 0. That means I1 into Q equals to I minus I1 into S. Divide equation number 2 by equation number 1, we get P upon Q equals to R upon S. Now, let us study the practical application of Wheatstone bridge. It is known as meter bridge. This is the diagram for the meter bridge. Here, this is the left gap and this is the right gap. In the left gap, we connect a known resistor R and an unknown resistance S is connected in the right gap. A jockey is connected at the central terminal with a galvanometer. We tap the jockey first at point A, then at point B. The galvanometer should show the deflection in the opposite sides. We move the jockey between A and B in such a way that we get a point where the galvanometer shows zero deflection. If the point P where the galvanometer shows zero deflection is at a distance L from the end A, then the length of AP is L and the length of BP will be 100 minus L. So, R upon S will be equals to L upon 100 minus L. Practically, we obtain the value of L and then we calculate the value of unknown resistance S. We can use the length of wire more than 1 meter. In that case, it will be called a bridge only instead of meter bridge. Potentiometer. Potentiometer consists of a long wire bent in the form of a wooden board as shown in the diagram. Point A of the potentiometer is connected to rheostat. Point B is connected to the positive terminal of the cell. If we have to measure potential difference across length Bj, where Bj is equals to length L, then potential difference V equals to K into L, where K is the potential gradient of the wire. This potentiometer consists of a long wire of given material having uniform area of cross section. If constant current flows through it, then potential difference across it V equals to I into R. Here R is the resistance offered by the total length of the wire. As we know, R is equals to rho into L upon A. So, we get V equals to I rho L upon A. As I, rho and A, the area of cross section, are constant, so we can say V is directly proportional to L, the length of the wire. Putting a coefficient of proportionality, we get V equals to K into L. Here K is a constant called potential gradient. Its SI unit is volt per meter. If we calculate the value of K, then we can calculate the potential difference across any section of wire. We know the value of K and any cell is giving a null point across a length L, then the potential difference across the length L will be equals to V equals to K into L. Application of potentiometer. A potentiometer can be used to calculate EMF of a cell. Always remember, we cannot calculate EMF of the cell with the help of a voltmeter. The reason behind it is voltmeter draws some current for measuring the value, whereas potentiometer works on null deflection method. That means it does not draw any current from the cell. So, we measure EMF using the potentiometer, whereas we measure the terminal potential difference of the cell using a voltmeter. Here is a diagram for the situation. If EMF of the cell is balanced across the length L of the potentiometer, then E will be equals to K into L. Here K is the potential gradient of the cell. Now, to compare EMF of the two cells, this is the second application of the potentiometer. If two given cells are of EMF E1 and E2, the two cells are balanced across the length L1 and L2 respectively of the potentiometer when the respective keys are connected one by one, then E1 upon E2 will be equals to L1 upon L2. There is an experiment based on this particular situation in the physics lab. Comparison of EMF of two cells. Two cells of EMF E1 and E2 are connected at point B as shown in the diagram. Always remember, all the positive terminals of all the cells are connected at the same point. When key K1 is closed and key K2 is open, then null point is obtained at J1, say length Bj1 is equals to L1. When key K1 is open and K2 is closed, then null point is obtained at J2, say length Bj2 is equals to L2. So, E1 is equals to KL1 and E2 is equals to KL2. Therefore, E1 upon E2 equals to L1 upon L2. Now, there is another experiment in the physics lab which is used to calculate internal resistance of the cell using a potentiometer. Here is a diagram for measuring it. The cell whose internal resistance is measured is connected with the positive terminal at point B of the potentiometer, and a series resistance S is connected with the key. When key is off, then EMF is balanced at length Bj1 is equals to L1. So, E equals to KL1. When key is on, then terminal potential difference V is balanced at length Bj2 equals to L2. So, V equals to KL2. Dividing EMF by terminal potential difference, we get E upon V equals to L1 upon L2. As we know, E minus V equals to I into small r. Here small r is the resistance offered by the cell internally, and I equals to V upon S. So, E minus V equals to V upon S into R. That means R equals to E upon V minus 1 into S. Substituting the values of E upon V, we get small r, the internal resistance of the cell, equals to L1 upon L2 minus 1 into S. When key K is open, then EMF of the cell E is balanced across length L1 of the cell. So, E is equals to K into L1. When key K is closed, then the terminal potential difference of the V is balanced across length L2 of the wire. Then V equals to K into L2. If the external resistance is S, then V equals to I into S. So, E upon V is equals to L1 upon L2. As we know, E minus V equals to I into small r. Substituting the value of I here, we get E minus V equals to V into R upon S. Again, substituting the values of E upon V, we get small r equals to S into L1 upon L2 minus 1. From here, we can calculate the value of the internal resistance of the cell. In this chapter, we have learned about Kirchhoff laws, meter bridge, Wheatstone bridge, potentiometer, and its certain applications. In the next session, we will study moving charges and magnetism. In the chapter, we will study Biot-Savart law, Ampere circuit law, and their applications. I hope you enjoyed the session today. Thank you.